We're going to take a look at sinusoidal functions, and this term applies both to the sine function and the cosine functions and any variant of those. We've looked so far at how the simple sine function would look, because we know that sine to 0 degrees is 0. Sine to 180 degrees is also 0, and sine to 360 degrees is the same as sine to 0 degrees, so that's a full cycle. Sine to 90 degrees is 1, sine to 270 degrees is -1. So when we draw the curve of the sine function, it's going to look something like this. And we could do the same for the cosine function. And cosine to 0 degrees is 1. And cosine to 90 degrees is 0. Cosine to 180 degrees is -1, and again 0 to 270, and cosine to 360 degrees is 1 again. So sort of the opposite of the sine function. And this is one period of each of the two functions. And it continues like this, so you can just add multiples of 360 degrees and you'll get this pattern. Now, when we use sinusoidal functions similar to these to mirror something, to model something in the real world, they would have to fit the data that we have, or to fit the phenomena that we have. So most of the time we want them to look slightly different from the simplest sine function and the simplest cosine functions. And what we can actually see is that the sine function can be written slightly differently. We can write it as a multiplied with sine to b x plus d, when a equals 1, b equals 1, and d equals 0. So if we put in these values for a and b and d here, we get sine to x. So that's the simplest form of the sine function. But these are called the parameters of the functions a, b, and d. And we can change these to make this function look different. We could do the same thing with the cosine function. So let's call this g of x, a multiplied with cosine, do that again, cosine to bx plus d. And if we put in the values 1, 1, and 0, we see that, this becomes 1, this becomes 1, so this is cosine to x plus 0. So it's exactly the same as this one here. But if we put in different values for a and b and d, this function is going to look different. Now we can think of these parameters as levers or buttons on a panel, so that whenever you change the settings of the function slightly, you can just push these buttons up and down, and it'll change the look and behavior of the graph. And we actually use these to make them fit the phenomena that we want to describe or model. Sorry about the coffee machine. Now we'll have a look at some definitions. Let's see, here we have them, A, B, and D. Whenever you change these, something is going to happen to either the amplitude or the period of the function or the principal axis. So in the next video, I'm going to use GeoGebra and we'll just see what happens to the function when we change the parameters. A sinusoidal function has a principal axis where one side mirrors the other, and whenever we want to, if we just want to draw sort of a general sinusoidal function here, where the graph looks like this, the principal axis is going to go through the middle like this, so that you get a mirror image on each side. Now we can find this principal axis by using the max value, which we find on top of the waves here, and the minimum value down here. So we find the principal axis by taking the y minimum and we add the y maximum, and then we divide by 2. So this is going to be a horizontal line, so that's why we write y equal, and then we put in these values and then we can find the principal axis. Now amplitude. Amplitude is the distance from, it's the vertical distance from the principal axis to any minimum or maximum point. So this distance here from the axis and up to any maximum point, or from the axis to any minimum point, it's going to be the same distance, even though it doesn't look like it here. But remember that the top is the mirror image of the bottom, so it's going to be the same distance. Now this is called the amplitude. And this again is the principal axis. So the greater the amplitude, the greater the waves of the function. If you have a low amplitude, you have small waves.